Hello everyone, my name is Nicolas Roussel. I am a researcher at the Navier Laboratory at the Gustave Eiffel University in France. And within the frame of this Rilem EAC webinar, I will have the pleasure of talking to you about Rheo-physics and shaping of fresh cement-based materials. My introduction will be short. I would like to draw your attention on the fact that last December, a paper in Nature stated that the global human-made mass has now exceeded all living biomass on this planet. So in other words, it means that everything we've built, everything we've extracted from the ground and transformed, everything we produced is now heavier than everything that nature has produced on this planet. Well, a big fraction, probably more than half, of this global human-made mass comes from construction materials, as everywhere it's possible, we try, all of us, to provide to people shelters or boxes to protect themselves from the environment. And among this construction material, there is one of these materials that is really leading and that is really dominating, and this material is concrete, or called as well liquid stone. Most of you are probably familiar with the stone features of this material, its hardened properties, its strength, and its durability. But today we'll focus on the liquid feature of this material, the way that this material flows, why it flows like that, what is its rheological behavior, and what is the relation between fresh properties and processing or shaping of this material. So to do that, we'll have two parts in this lecture. In the first part, I'll speak about rheology and the underlying physics at the origin of this rheological behavior. And in the second part, I will more focus on material processing and try to show you that if we accept pumping and mixing, that I will not speak about today, material processing or material shaping for concrete is a competition between gravity-induced stresses and the consistency of the product. Well, of course, it's a very large, wide topic. I won't have time to speak about everything. So I'm providing you here some keywords linked to this topic that you can use to find some relevant literatures, and I'm suggesting here 4 books from the first rheology of fresh concrete from Tattersall and Bonfield in the 80s to the last one, theory of application of colloidal suspension rheology, with a full chapter dedicated to cement-based material by Wagner and Mewis. Well, let's start with something typical of rheometry, the flow curve. So flow curve is what people doing rheometry do plot. It's shear stress as a function not of a deformation like we do for solids, but as a function of a deformation rate, the speed at which you deform the material. What people do plot as well is apparent viscosity, the ratio between shear stress and shear rate as a function of shear rate. So in such diagrams, water, a Newtonian liquid, would look like this. So a constant apparent viscosity, a constant viscosity, Newtonian viscosity, and of course a shear stress that increases linearly with the shear rate. Well, cement-based material look very different. And the main feature that we will spend some time on today is the fact that this material displays a yield stress. So it means that you need to apply to this material a critical stress above a threshold for the material to flow. And above this yield stress, the material flows and its viscosity decreases with the shear rate, and this is called shear thinning. If you go at higher shear rates, you can even reach a Newtonian plateau where the material looks like a Newton fluid, but this corresponds often to shear rates that are not of interest for the industrial practice. So we are mostly facing a yield stress material with a shear thinning behavior above the yield stress. Let's try to discuss the origin of such a behavior. So to do that, I'm going to focus on the cement particles that are at the origin of the behavior. The sand grains, the gravel, have been shown to only amplify the behavior at the level of the cement particles. And we have at this level particles from 100 nanometer to 100 micrometer for the coarsest. They are mixed with water. And the phenomena at stake that have been identified are Brownian motion or thermal agitation, gravity potential energy due to the fact that there is a difference in density between the cement grains and the liquid, and colloidal potential energy for this type of size. 100 micrometers is quite big for colloidal particles. 100 nanometers is really a good range. And these create some non-direct interactions, repulsive or attractive. Well, in the case of cement, all these phenomena are studied in detail. So we often choose to consider as a reference Brownian motion or thermal agitation, because it's something that can be easily assessed. And we have as well some colloidal interactions. They were shown to be mostly attractive van der Waals forces. And in fact, they do not take much into account the diameter of the particle. They are more concerned with the diameter or the equivalent size of the asperities on the surface of the cement grains. And we have as well, of course, as already discussed, some gravity potential energy that could induce a sedimentation of the cement grains. It is possible to get an idea of the magnitude of these various energies or potentials and to compare them. That's what we do here. So, as already stated, I take as a reference the thermal energy, kT, K being the Boltzmann constant and T the temperature in Kelvin, and I compare that to the two other potential or energies in the system. So, first thing, gravity potential is systematically higher than thermal energy. This means that thermal energy is not able, through thermal agitation, to maintain the particles in suspension. So, as a consequence, cement suspensions are unstable by nature. So they do sediment, they do consolidate, and we expect these particles to be either too coarse or too heavy to be stable. In parallel, the attractive van der Waals potential is systematically far higher than thermal energy. So it means that particles will get attracted to each other and form flux. And these flux are stable, because thermal energy is not able to destroy this flux through thermal agitation or thermal dispersion. Finally, if we have enough particles in the system and that they get percolated through the formation of this stable flux, then the system will get a macroscopic yield stress that you will need to overcome for the particles to move relatively to each other and for flow to start. And last but not the least, gravity potential is systematically lower in terms of magnitude compared to the attractive van der Waals potential. It means that the flux that are being formed are stronger than the gravity-induced potential, and it means that these flux have the potential to prevent phase separation or bleeding and make the system stable. So all in all, cement pastes are unstable by nature because cement grains are either too heavy or too coarse to be suspended in water. But particles do flocculate because of some attractive van der Waals interaction at the level of the cement grains surface default or surface asperities. If there are enough particles in the system, so it means a water to cement mass ratio that is low enough, the network of interacting particles is at the origin of a yield stress. And this network is so strong that it is able to keep the particles captured, preventing them from moving, which allows the system to become stable and which allows providing a cement-based or cement-based material that can be used by industry because it is stable. However, we cannot forget that cement powder is a reactive powder. And even if we are in the dormant period and all chemical reactions at this level, at this stage, are often neglected, it has been shown that there is a lot of dissolution and there is a lot of nucleation. And this nucleation happens at the pseudo-contact points between the flocculated cement grains. So as a consequence, in the first 10 to 100 seconds, the particles will flocculate through a diffusion aggregation process typical of colloidal suspensions. And after that, the system will be reinforced by the nucleation of this hydrate at the pseudo-contact points. So what matters for us and for the second part of this presentation is that after mixing or after flowing, when the material is at rest, we build a yield stress because of two mechanisms. One of them is flocculation, the second one is structuration through nucleation, and all in all, the yield stress is increasing with time. So let's move to the second part, material processing, and I'm going to come back to this picture I used because I think it illustrates quite well the fact that concrete industry is mostly a molding industry. So for a long time, the main dominating shaping process that we use is molding. So in most cases, everything goes fine. Gravity, the density, the weight of the material is inducing stresses inside the material that are strong enough for the material to flow and fill fully the mold. In some other cases, unfortunately, it is not the case, and you can find some voids or some defects that even vibration is not able to make disappear. So to analyze that, the main idea of this presentation is to speak about gravity-induced stresses and compare these to the consistency of the material. And we're going to have three parts. The first part, gravity is your only partner. Gravity is helping you shaping the material. The second part, gravity is helping you, but gravity is not enough. You need to bring some additional energy. And in the last part, gravity becomes your enemy and consistency needs to be high enough to fight against gravity. So, to do that, we're going to use only one relation. It's a very simple dimensionless relation that opposes the consistency on the left and gravity-induced stresses on the right. So we are in the first case, gravity is your only partner. If gravity is playing a role, then density, of course, appears in the right part of the equation, and it is competing with yield stress or consistency of the material in Pascal. For this relation to be dimensionally correct, we need here a typical length scale of the problem, and this length scale is teaching us many things. So first, an illustration of this relation, of a famous test that is really representative of the first attempts to measure rheology for cement-based materials, slump or slump flow. So what we have is a material in a cone, and then suddenly we lift the cone and the material flows. It flows because the stress induced by gravity is higher than the yield stress of the material. So it starts to slump, and as it slumps, then the typical length scale, which is here the height of the sample, decreases and the flow slows down. It slows down until the stresses induced by gravity inside the sample are equal to the yield stress. So it means that we have here an illustration of this very basic relation between a length scale and a yield stress, and we have here the explanation why this test is so efficient at capturing the yield stress or the consistency of a given cement-based material. Another consequence of this relation is the so-called self-compaction. So I'm coming back to this relation, yield stress on one side, typical length scale on the other side, and I try to imagine now the value of the yield stress, below which I can feel all the molds, and I can feel all the delicate and narrow parts inside the molds, between the steel bars, for example. So what is the critical value below which I will be fine, and gravity will be sufficient to cast anything? So this length scale is of the order of a couple centimeters, and it means that the yield stress for typical density concrete should be around a couple hundred Pascal. And this indeed is the yield stress of self-compacting concrete or self-compacting mortar. A yield stress that is so low that the material is able to fill most formworks, even the most complicated one, to go through very dense steel bars. But keep in mind that we can't design materials that have no yield stress at all. That would be perfect to fill anything, but with no yield stress, we're going to face the difficulty we have already discussed, stability. We need a yield stress at the level of the cement paste for the cement paste to be stable. Moreover, this cement paste needs to carry the aggregate in the suspension. So we will always need a minimum value for this yield stress. But if this yield stress stays lower than, let's say, 100 Pascal, we are able to fill most mold, most formwork in most conditions. Let's move now to our second part, when gravity is not enough. So in this case, I'm going back here. Density cannot be changed. If you have difficulty casting a given cement-based material, you won't change the density because of that. The typical length scale is imposed by the object you want to produce. And you can play on two things, yield stress or gravity. The thing is that you could decrease yield stress by using admixtures, which is out of the scope of this lecture today. But if you don't want to change mix design, you can change yield stress by using internal vibration. Internal vibration, the insertion of this vibrating pocket inside the material, imposes locally a high frequency periodic shear rate, and it destroys the structure material, destroys this network of interaction at the levels of the cement grains, and the yield stress turns to zero and for a short time and ease the placement of the material, with of course the risk potentially of instabilities of the material if you vibrate it too long. The other possibility is external vibration. With external vibration, you don't touch the material really, but you replace the acceleration of gravity by an artificial external acceleration where you have a dependency on the amplitude that is often limited because we are trying to vibrate very heavy, a very big object, and the frequency. Here we are speaking about things with amplitude around 1 millimeter and frequency around a few tenths of hertz. But this often in precast allows for a perfect molding of the system when gravity is not enough to have a full molding and a full flow of the material inside the mold. The last part deals with the case where gravity is your enemy. The most obvious example is spraying, okay, or rendering. You can apply a mortar, that is what I show here. You can as well apply concrete, internal lining. And in this case, the problem is still using the same relation, except that this time the yield stress must be higher and not lower than the gravity-induced stress. For the material to stick on the wall, for example, this 2 cm layer of render mortar, the yield stress must be at least equal to 300 Pascal. And this is the first case where you, in fact, have to fight against gravity. You want the material, because of its consistency, to be able to resist gravity, whereas before gravity was the stress pushing the material inside the mold and guaranteeing that your process and your shaping will be fine. The second example that is more recent is extrusion-based additive manufacturing, or so-called 3D printing. So in such technologies, you have a robot allowing you to deposit some material layer by layer until you build a 3D object from scratch, and the freedom of shape is amazing, and the possibility to build different structures is something that really needs to be explored. I'm giving you here a few values about the layer thickness, which is called as well the resolution of the printing. 10 centimeters is when you print concrete, 1 millimeter you are mostly printing grout of paste. The layer width is varying as well. You can print up to 3 meters in most cases. We could go higher, but I don't have examples. And you can even print house with a printing perimeter around 50 meters. And the printing rate, not for houses of course, but for columns, can go up to 10 centimeters per minute. Here, I'm going to show you an example. So this is the way that the material is printed in the Technical University of Eindhoven. And we can see that first we need the material to have a yield stress that is high enough for the layer that is deposited to be stable, to have a control shape. But then the stress inside the system is increasing as you print, because you are superimposing layer by layer, and the gravity-induced stress is progressively increasing. So let's first have a look about the yield stress that is required for the layer to be stable. We have two cases. Some people do some free flow deposit where the material is very fluid and then builds up a structure because of this thixotropy, nucleation, structuration. And on the other hand, you have people printing what is in a mode that is called infinite brick extrusion, where the material yield stress is quite high, and the material shape is mostly controlled by the initial consistency of the product. Well, here we have, at the level of the deposition, a target window for yield stress. So it means that the yield stress of the material must be high enough for the layer to have a control shape. At the same time, there is an upper limit because some artifacts or some problems do appear when you have a material that is too stiff. For example, if your stiffness is too high, you can have some local cracking in the sharp angles that are being printed, also local elastic instabilities at the level of the printing head if there is a slight difference between the extrusion velocity and the robot velocity. But all in all, we can still apply the same relation between a gravity-induced stress, but that this time is increasing with the number of layers that have been printed, and the consistency inside the first layer. And this would require that the yield stress of the material increases linearly with the printing time or with the height of the printed element. So here we are facing a technology that requires different values for the yield stress, at least a value that is evolving with time, which is perfect for cement because cement naturally is changing with time as we discussed previously. However, the values you need to reach are quite high, so it means that this kind of change is mostly induced by some chemical hydration or some nucleation of minerals. And the other problem is that the main reason for failure during printing is not often a plastic failure of the first layer. It is often an elastic instability or so-called buckling of the entire object being printed. And this is called self-buckling. It is the same phenomenon as the one that dictates the maximum height of trees on this planet. And the particularity of this is that for the first time it prevents us from using this very basic relation between consistency and a typical length scale, because buckling involves the height of the object at the power 3 and not at the power 1. So it means that when you print, you need a yield stress that is in an initial window for the filament or the layer to have a control shape. Then you need this yield stress to progressively increase with time or height so that it is able to support the weight of the layers above. But at a given critical height, you switch to a buckling failure regime that forces you to have very high values for the consistency of these materials. So all in all, cement-based materials are yield stress and thixotropic materials. They build up a structure with time, either due to flocculation or to nucleation of hydrates. Their yield stress behavior is dominated by adaptive van der Waals forces, but they prevent the material from being extremely fluid, but they allow the material to be stable. The thixotropic behavior finds its origin in some hydrate nucleation at the contact points in the colloidal network, and adsorbing and non-adsorbing macromolecules allow for the tuning of the rheological behavior to the process, but that is something that I will not, and I have not talked about here today, but that is one of the books that I suggested in the introduction. And concrete shaping has always been and is still the result from a competition between gravity-induced stresses and consistency of the material. And with that, I thank you for your attention.